So yeah, so the important thing to remember, at least for Lorentz transformation, right, is there's two frames. So we just need to know which observer is on which frame, and wait ah, is out of focus. Hang on. It doesn't work. Okay. Oh, nope, Kaheng, you haven't missed anything. So haven't even started. Yeah, I was still struggling to focus my projector. Oh, yeah. So this type of thing, you need time to process in the brain. That is definitely true, especially for things like relativity. What is? Huh. It's a bit strange today, but I think okay. So now it looks good. Yeah. So now we get started. As I said, right, this is the final week already. We are finishing the syllabus. This is the last important topic of special relativity, and then we will we will probably finish everything today, and then still got one more class on Wednesday. So we shall probably spend the whole of Wednesday doing tutorial questions or whatever things that we left behind. So if you are still confused or anything, right, this is actually a good chance. If you have any question, then you ask me. Maybe I will compile all the questions, and then any concept that we want to cover again on the Wednesday class to review again, we can do that. Otherwise it's gonna be a very short class, right? We will finish all the topics probably today, hopefully. We shall see. Okay, so right now we have so in the past week we have been learning about special relativity. We have Alice and Bob, right? So Alice measures a time and position of a certain event. Bob will measure his own time and his own position at a certain event. So we've got two different coordinate systems, and using Lorentz transformation, we can predict what will Bob measure based on information. If you're Alice, right, and you know how fast Bob is moving, the Lorentz transformation will tell you what Bob will measure without having to ask Bob, right? That is the formula for Lorentz transformation. And we have also learned how to transform velocities and things like that. Okay, so remember, right, when we discuss motion like positions, velocities, and all those things, that is the subject that we were calling kinematics in chapter 1. Kinematic is just to describe how the object moves, and the dynamics and mechanics is Newton's law and things like that is to explain why the object moves. That is what we want to do today. So mechanics, but we need to account for special relativity, because, right, why does Newtonian mechanics change because of relativity? Because the reason is time changes. When we talk about Newton's law, right, Newton's law, F equals to ma. The a contains acceleration. So acceleration is the second derivative of position with respect to time. So there's a position and time there. So it changes. Because of special relativity, we know that position and time is affected by your relative motion with the object and other frames and things like that. So we need to account for this correctly. Okay, so so one of the so we can say that we will try to now do that properly, but as I said, right, we will not derive the formula from scratch, and hopefully it's good news for you guys. So less mathematical details to worry about. I will just tell you the formula for the momentum. So right now, right, let us consider, because we are just consider observing a particle as Alice only, so we don't need to confuse ourselves with Lorentz transformation for the moment. Okay, let's say we are just having one frame, we are Alice. Okay, so Alice, we are using frame S. Okay, and we are observing a point, point P. Okay, so this point P is a particle having mass m and velocity v, measured by Alice, of course. Okay, so when we talk about relativity, right, we always need to check who is the observer. But for now, it's easy. We only got one observer, and for the moment, we shall consider x direction only. So even make everything simple, just less things to worry about. X direction only. Okay, and let me now define. If Alice is observing a particle that is moving with velocity m, wait, am I recording? Yes, I am, right? Yes. Someone raise your hand. Do you have a question, Iran? Or accidentally press? Yeah, so let me know if you have a question. So we are Alice, we are observing a particle P that is having mass m and then is moving at velocity v, right? Because we are talking about particle P, we are not talking about Bob. So P can be accelerating, that's fine, right? P is not the frame. We only look at our own frame. So we are an inertial frame, and then we are observing a particle that may or may not be accelerating. So we can define the momentum of that particle that is relativistic. So we call this relativistic momentum. Okay, so relativistic momentum is given by this. Okay, so relative momentum of point P observed in Alice frame, which is S. Actually, here is everything is only got S, and is given by P is the normal momentum, but we are dividing by this term. So 1 minus v squared over c squared. So v is the velocity of the particle, right? So v is the velocity of the particle. So v is dx dt is velocity of P measured by Alice. We are only talking about one frame, but since we are in relativity, right, we should always it's always good to specify. And obviously x is the position of P measured by Alice. Okay, so this is the formula for the relativistic momentum. Miss Tasha, okay, yeah, so no problem. The raising hand is next to something, so usually people will accidentally press. So yeah, so that is the definition of the relativistic momentum. So if the particle is moving very slow compared to the speed of light, this factor is close to 0, so this term is close to 1, then we get the ordinary momentum. So that is the observation here. So if P is moving slow compared to the speed of light, compared to C in Alice frame, right? So every time we say slow, right? But slow compared to what frame? We are talking about frame measured by Alice. So that my V is smaller than C, then this factor is approximately equals to 1, then my momentum is back to mv, the ordinary momentum, right? So this will come back to the original momentum if I'm moving very slow to the speed of light. But if I'm moving very fast to the speed of light, it's not just mv, but mv divided by this thing. So this one is something similar to the Lorentz factor, but this v here is the velocity of point P. Okay, so it's not exactly the Lorentz factor, but it's something similar. Okay, so we got this formula now, and then another comment. because a lot of you have been asking about things that mass increase when the speed is going very fast, right? And I say that is something that we don't agree, because in physics, right, for physicists, mass is constant also, regardless of the frame. That is also true. It is an invariant quantity. Ignoring quantum mechanics, right? In quantum mechanics, you got effective mass. I think that is a separate reason away from well, you need special relativity and quantum mechanics to say that. But sometimes people say, right? So I would say some people say mass increase when V increase. I want to explain why people say that. Okay, the reason is because P is equals, because this is the definition of relativistic momentum. And then the reason why these people say this is because they still want to define momentum as mass times velocity. Okay, so then that means they want to take a velocity and then they want to say something else that is mass. So what they do is they call it this as the effective mass. Okay, so V. Okay, and then this one is some people call the relativistic mass. Okay, and then this is equals to m relativistic and then V. So the relativistic mass is changed by the factor, and that is why people say, because as V increase, right, this number is smaller than 1. So if the mass divided by smaller than 1, then the relativistic mass increase. So this is the reason why people say mass increase when the speed increase, but it's not really the mass, it's just mass divided by this factor. Okay, so we will not do it this way. Okay, so we won't do it this way. Okay, to us mass is mass. To us mass is mass, m is the only mass. Okay, so we don't talk about relativistic mass and things like that. We talk about relativistic momentum. Okay, and why we do not use this to be consistent with momentum is because, right, this is not the complete definition of momentum. Even for objects slower than the speed of light, right, momentum is not always given by mass times velocity. So you will learn more on this in your year 2 when you take the classical mechanics in year 2. Okay, so the definition of momentum as mass times velocity is only for linear motion, which we study in chapter 3 and 4. And for other cases, we still have momentum, and it will no longer be this. So the true definition of momentum is defined by the Lagrangian. So that's why we do not talk about this relativistic mass. Okay, so the momentum is affected by this, but mass is still mass. Okay, so that is why. There is a proof. You mean talk about momentum, right? Yeah, we are not going to prove it, but yeah, so what I say is the reason why we got this is in this section, which I put a star there, which means it's optional. So it's not examinable, this chapter, but yeah, so we will derive all this and we will come to wait, did I forget to include? There's the 4 velocity and things. I think I forget to include. So for those who are curious, let me include this in. I think I accidentally deleted it. Yeah, because it's not examinable. So yeah, so we shall take it as a definition. Most object in everyday life is slow compared to the speed of light. Yes, correct. So the reason why we can spend so much time in chapter 1, 2, 3, and 4, right, to talk about momentum, the Newtonian momentum, is that most objects travel slow compared to the speed of light. Yeah, cars, aeroplane, race cars, things like that. Actually, all these are very slow compared to the speed of light. And in the examples that we solve, right, things that are moving very, very fast compared to the speed of light is very rare situations, but they do happen, right? The cosmic rays colliding with the atmosphere and then they spray particles that are very fast. Or the particle accelerator in CERN, Switzerland, or LHC, or the linear collider, they also travel, those particles travel very fast compared to the speed of light. Or around black holes, right? So the jets coming out of the black hole, they move very close to the speed of light. So those are the few cases. But everyday life, in our everyday experience, yeah, they move very slow. So yes, I sound like him, right? Was it the original one? He's saying math is math, right? Yeah. So oh my god. So this is childhood for you guys, ah. Wow. Yeah, then I feel very old. So for you guys, The Incredibles is a childhood movie. Oh my god. I'm super old. Yeah, so math is math. Yeah, so we just take this. In fact, right, yeah, that's why we can have a well-defined mass of the proton, mass of the electron, and then when we use special relativity and then we collide them, we still use that value of mass. Okay, so it's not really it's not really affected by the speed that is traveling in. Okay, so we got the relativistic momentum. Now we want to solve what happens for the relativistic force. Okay, so for the relativistic force, we shall use the definition that still works. In this case is, yes, the force, right, is still the rate of change of momentum. That is still true in this case. So this is the relativistic force. So that means, right, remember there's a t here, and remember we are only using Alice, so this is the t that is used by Alice, so we can apply everything normally. Okay, so this time is Alice time. Okay, and then the p is the momentum in Alice frame, so p in Alice frame. So everything is in the same frame, so we can use the same variables and calculate them together. No need to do any Lorentz transformation here. So that means, right, I'm differentiating p with respect to time. So that means I'm differentiating p. What's my p? My p is given by this formula. So I'm differentiating mv over 1 minus v squared over c squared. Okay, so now this is where you do derivative, right? So if you're learning the calculus, this is what you've probably been doing this a lot. How to do this? You can do it by the quotient rule or the chain rule, right? So I shall do it the chain rule way. So this is v times 1 over this. So I will differentiate the v first. 1 minus v squared over c squared. And then I differentiate the bottom in the second factor. So the second factor is 1 over this. So I got 2, 1 minus v squared over c squared. And then to the power 3 over 2, right? And then there's a mv that is untouched. And then I need to continue differentiating whatever that is inside chain rule over here. Okay, so let's hope I didn't make any mistake. Let's see what we got. This is m dv dt, right? And then this is 1 minus v squared over c squared, the square root. This one I can simplify. The minus will cancel out, and then this is mv. So if I differentiate, right, c is a constant, so you can't differentiate it. It becomes 2v over c squared. And then there's a 2, and then 1 minus v squared over c squared to the power 3 over 2, right? So the 2 and 2 will cancel also. And what we have, oh yeah, differentiate v already. I forgot, right? The variable is t. So differentiating v, I still got the chain rule. So I got a dv dt at the back. Okay. So what I have now is that, well, that's a dv dt. So what's dv dt? dv dt is acceleration, right? So dv dt is acceleration. So we have dv dt, acceleration measured by Alice, right? So everything we are using Alice frame. Okay, so that means dv dt is the second derivative of the position of point P. Okay, everything in Alice frame. So what we have now is ma 1 minus v squared over c squared bracket plus I have mv squared over c squared, and then there is a here, 1 minus v squared over c squared to the power 3 over 2. So I want to, to simplify this, let us make the denominators the same. So I shall times this by 1 minus v squared over c squared. So both factors now will have to the power 3 over 2. So top and bottom I times by v squared over c squared, and then plus there's a ma which are the same, v over c squared. So I can factorize this. So what I have now is 1 minus v squared over c squared plus v squared over c squared. So they cancel each other just nicely to the power 3 over 2. Okay, so cancelling, and then finally on the right hand side was force is trying to get the derivative with respect to momentum, right? So I have my expression for relativistic force now, which is just ma, and then is this thing to the power of 3 over 2. So this is my relativistic force. Okay, so this is the force in for objects moving very close to the speed of light. Yeah, definitely generation gap. Yes, quotient rule or product rule is actually the same. Yeah, quotient rule. Right, so if you remember quotient rule, right, if I differentiate a over b, right, so it's b square differentiate a times b and then minus ab prime. Okay, but what I did just now, right, is, well, I pretending that it's a product. Sometimes it's a habit lah. So it's a times 1 over b. Okay, and quotient rule is the same as the product rule. If I consider the inverse of b is the same as this, so it's a prime times 1 over b plus a and then minus b prime over b square, right? So if you make the denominators the same, you get back the same thing, a prime b minus ab prime. See, so these two, there's two ways you can do it. I don't know why I do it in the second way. Probably faster if you do it this way, I think. Yeah. But anyway, yeah, as long as we get the expression right. So we got the relativistic force now. Okay, so this is page 2. Yeah, so if if the particle is accelerating at this acceleration measured by Alice, then this is the force that is experienced by the particle. Okay, so we can again check, right? So if my velocity is very slow, then this term is close to 1. So for low speeds, right, which is where v is much smaller than c, like our everyday object, just a normal car driving, right, a few 100 meters per second, even like aeroplane or things like that, few 100 meters per second is going to be a small number compared to c square. Okay, so that means v over c is a small number, small, right? So that my force is just ma over 1 minus a small number. So you got this. Okay, so we got back to Newtonian momentum. As long as v is much smaller than c. Okay, so Newtonian mechanics is still correct. We can still use Newtonian mechanics even for as long as my particle is going very small compared to the speed of light. So this is why we did not start teaching special relativity in this course starting from chapter 1. Even though we say that actually the special relativity, right, is the more correct theory, because special relativity is consistent with our experimental observation that the speed of light is the same for every frame, right? But that is only for measuring speed of light. But Newtonian mechanics in that sense is wrong, because if you use Newtonian mechanics, the Galilean transformation, we get a result that is not consistent with experiment. But why do we still use Newtonian mechanics? Is because most of the time v is much smaller than c, then everything is correct. Then it's still correct, so we can still use it. Yeah, you mean some of you still want to do a bit more math, right? Yeah. So yeah, I kind of like cut down the math a little bit because I jump straight to the result. Okay, and so I would suppose the MAT student would prefer more math, but then our physics student will be scared away. So I don't want to scare you guys yet. So yeah, usually for physics students, they learn math a bit more. The advanced math they will learn a bit more later, and that is where all the advanced math stuff comes in. Math. Why is the light same in all frames? Actually, it's well, you can put it in that way. I would say we don't know why. It's just that we think the Michelson-Morley experiment, they did a measurement and then they measured the speed of light in this direction, in that direction, that the earth is moving or the earth is rotating. They always get the same value. Why is that so? Well, we can't. It's almost becoming a philosophical question. But the why also comes from math lah. Is because in flat space-time, our space-time is having a Lorentz symmetry group. Yeah, so you don't know what that means. It's because we need to learn. It's a bit of a group theory. Yeah, so correct. It's experiment. Yeah. Yeah. So why is the speed of light the same in every frame? It's hard to answer. We can sort of like, I think there are some theories that derive this result, but it's hard to make any progress, because to make more progress we need to do more experiment in that domain, and measuring speed of light is very difficult, right? So we need like high particle velocity and all those kinds of things. Okay, so yeah, so that's why in special relativity we put it as a postulate, right? Postulate is just, okay, if this is true, what are the consequences? So if all this is true, we derive the Lorentz transformation and things like that. Why is that true? It's at the moment it's hard to say. Okay, yeah, so that is the reason why. So okay, so we so at the moment, right, we have a formula for the force, okay, which is ma 1 minus v squared over c squared to the power 3 over 2, and let's see what okay, yeah, no problem. It is an interesting question to think about, right? Why is light speed? Why is light special? Actually, not to say light, but why does the universe have the maximum speed limit? Yeah, so not sure. It's hard to say. In fact, most of the physical theory is built based on the postulate. It's like, assuming this is true, what do we get? And why did we assume it's true? The Michelson-Morley experiment. And since those days people do more and more accurate experiment, it still seems to be always true. So yeah, so let's continue with this now. Let's talk about acceleration and why we cannot go faster than the speed of light. I kind of mentioned this a little bit in the Lorentz transformation already. We can even see this here also. So let's say a particle p, right? Can I accelerate a particle p that is going beyond the speed of light? So let us try to calculate the acceleration. So if I want to calculate the acceleration, I bring the mass down, and then I bring this up, so I got v squared over c squared to the power 3 over 2. So observe that for special relativity, right, especially if I go faster and faster compared to the speed of light, the acceleration depends on the velocity. Okay, so if I want to go faster and faster, my acceleration actually is reduced because now my acceleration is velocity dependent. So if my acceleration approaches the speed of light, and assuming f is not infinity, obviously, then what happens if I take the limit of v approaches the speed of light? Okay, so if f is finite, m is the mass of the particle, so it's fixed, so it's 1 over m, and then I take the limit of v approaching c of f, 1 minus v squared over c squared to the power 3 over 2. So if f is not infinity, right, then finite number times this limit that is going to 0. So this limit goes to 0. Okay, so acceleration 0. So when particle reaches speed of light, acceleration becomes 0. When the particle approaches speed of light, acceleration approaches 0. Remember, what is acceleration? Acceleration is the rate of change of velocity, right? So if I go to speed of light, it seems like acceleration goes to 0, so it will force it to become constant speed, so I cannot accelerate anymore. Okay, so if acceleration is positive, right, then the rate of change of velocity is increasing. The velocity is increasing, but when I approach the speed of light, this rate is 0, so I cannot increase anymore, so cannot accelerate. So this is the reason why we cannot accelerate beyond the speed of light. Okay, so how do you get a non-zero limit over here? Either, well, this limit goes to 0, right? Either m is 0, massless particles, or force is infinity. So you're going to need an infinite force to accelerate a particle beyond the speed of light. So yeah, where can you find infinite force, right? Cannot. So that is why nothing can go beyond the speed of light. So that is another reason why we cannot go faster than light. Okay, any other question? Yeah, so we are quickly finishing all the topics already. What else haven't we discussed about relativity? We actually have not discussed the famous formula, right? What is the famous formula by Einstein? The E equals mc squared, right? So actually, I saw a post on Facebook that there's a coffee shop that has the name E equals mc squared, and he called it energy is milk and coffee square. So I don't know if you've seen this on the internet, but I just saw it like yesterday, and then I should have saved the picture since I'm talking about this today, but I forgot. So let us talk about let us derive the formula, right? Why is E equals mc squared? What does that mean? Okay, so by the formula itself, right, it says that the energy is related to mass times c squared. So the common interpretation of the formula is that mass can be converted into energy, and that is also one of the central implications of relativity, and also it will carry over into general relativity as well. Why is this interesting? Because, right, if mass can be converted into energy, then energy can be converted into mass. So what is the implication? What is mass? Mass, right, if you learn gravity, mass will attract object towards itself by the gravitational attraction. So mass is a source of gravity. Then energy can be converted into mass. So anything with energy can be converted into mass, and therefore anything with energy can be a source of gravity as well. That is also very interesting. For example, a magnetic field, right? Magnetic field, you will learn in next semester that a magnetic field carries energy itself, and because of this, then magnetic field itself can also act as a source of gravity. So that is a very strange implication of special relativity. So electric fields and magnetic field can carry energy, and therefore gravity. Okay, so that is what we want to derive today. The formula for E equals mc square. So this is this part, 10.4.2, relativistic work and energy. Okay, so relativistic work and energy. Before I begin, let me check the questions. So you guys also saw, right? Yeah, I think a lot. It was in at least Malaysian Facebook. A lot of people were sharing it around. Then a lot of people saw it. So yeah. So what's the work done by relativistic force? So that is what we want to calculate. If we want to calculate energy, right, we start with the work done because we have relativistic force already. So we have this force. So what is the work done? Okay, so work done by relativistic force. Okay, so yeah, we the formula is still holding, is like this. So the integral of f with respect to dx. Okay, so but now instead of, this is the definition of work, right? But now, right, we are including special relativity. So the force is not just ma, but it contains dividing by v squared over c squared to the power of 3 over 2, right? And I integrate this with respect to dx. So I want to calculate. So if a particle that is experiencing a force, right, what is the work done on the particle? So therefore, if we know the work done on the particle, we can know the change in energy of the particle, because the definition of work done is to calculate how much energy has been transferred in or out of the particle. So that is what we want to calculate over here. So how do we do this? We do it the same way as we did last time, just that I got this additional factor down here. So what did we do last time? We change variables, right? Instead of integrating x, we change variables to v. Then we integrate, we got something with the mv square, right? So that was last time. We still want to change variables to v, but now I got this factor. So let's change the variable first. So my acceleration is the rate of change of velocity, right? No problem there. So therefore my a dx is dv dt dx. And what is dx? So dx also change variables. Dx is dx dt with respect to dt. So I can put it like this, right? So I got dv dt, and then I got dx dt, and then dt. So I rearrange. So I'm going to keep this as my variable. So I got dx dt, and then I put this together. So dv dt dt is just basically dv, right? Yeah, calculus change. A combination of chain rule in calculus, and this is defined as the rate of change of velocity. Okay, so we have shown that a dx is equals to v dv. Okay, so I will guess this might work as a calculus question. If I were teaching calculus again, I will probably set something like this, right? It's quite useful and quite important. Well, at least for physics, right? So let us plug this in. So my work done, right? So my a dx is now v dv. So my a dx, I will change this into v dv. So my work done is the integral of m v dv 1 minus v squared over c squared to the power of 3 over 2. Okay. So now this is the integration with respect to v now. And how do I integrate this? Again, this is more calculus stuff, right? So I don't want to waste too much time. I will just say that the antiderivative is the integral of this function, right, is actually mc squared. So the mc squared start to come out already. Okay, so let's check. What do I mean is that if I differentiate this, right, I will actually get this back. So let's check. Okay, so differentiate this. My variable is v, so differentiate this with respect to v squared over c squared. Mc squared is a constant. So I'm just differentiating 1 over the square root. So differentiating 1 over square root, I will bring down a half. And then this one, the power downstairs increased by 1. So I got v squared over c squared. Power increased by 1 becomes 3 over 2. And then if I differentiate, I need to differentiate the chain rule. So I got mc squared. There's a half. There's a 2v over c squared negative. Oh yeah, if I differentiate this, I should bring a negative power, so that at the end is going to be positive 3 over 2. So cancelling the 2, cancelling the minus, and cancelling the c square, I got this. So in other words, d dv mc square over 1 minus v square over c square square root is equals to mv dv, mv over. Right, so differentiating this, get this. So in other words, integrating this, therefore the integral of this function is equals to this. So mc square square root. Okay, so I skip the calculus. You can probably do it by integration by parts or whatever. Yeah, never mind. I just want to convince ourselves that this is the correct formula. So we got this result. Okay, so this is a work done by the relativistic force. Okay, so work done by relativistic force. And well, how to calculate the energy change? Okay, so we shall put in the limits of integration. So let's say a particle is having some initial velocity v1. It could be at rest, so I got v1, and then end up at some later velocity v2. So if I integrate this, I should put in the limits v1 and then v2. Okay, so if I integrate, right, what do I get? So this will becomes mc square 1 minus v2 square over c square square root, and then minus mc square 1 minus v1 square over c square square root. Okay, so this is something minus something. Now remember, when we were doing chapter 3, right, when we're talking about the work energy theorem, we define this as the change in kinetic energy, but we will realize that, you know, we cannot call this quantity kinetic energy anymore. Okay, so if at this stage, right, if we were following the methods of Newtonian mechanics, at this stage, if you check back what we did in chapter 4, right, we integrate the W, and then we define the kinetic energy to be the antiderivative of the force with some antiderivative of this thing, right? So this minus this, so we will define this as the kinetic energy, right? So at this stage, we would define mc square as kinetic energy. But we cannot do this here. Okay, so we cannot do this here, and I will tell you why. So why can't we do this here? Kinetic energy is supposed to be, we wanted kinetic energy to be something associated with movement, right? So that when the velocity is 0, the kinetic energy is 0. But for this case, right, cannot, because when the velocity is 0, this term is non-zero. Okay, so it doesn't work. So I shall write more sentences here for future reference. We cannot do it here because well, mc square 1 minus v square over c square, okay, is not 0 when v equals to 0. So in fact it becomes mc square. Okay, so it's not the kinetic energy. So what kind of energy this is? So according to special relativity, right, even for object in zero velocity, it is still having some value of energy. It's called mc squared here. Okay, so we can't call this kinetic energy, but let us call this quantity, like energy. Just call this energy first. Okay, so that my E is equal to mc squared, and then 1 minus v squared over c squared. Okay, so we shall just try to call this total energy for now. Okay, so according to our calculation, this is the energy so it's not necessarily kinetic energy anymore, but it is some quantity, right, that we got from our special relativity calculation. It is some energy carried by a particle of mass m and having velocity v. Okay, so for a stationary particle in Alice frame, so that means if v is equal to 0, then my energy is equal to mc squared. So a stationary particle also still contains energy, and that is kind of an amazing quantity, because when we are talking about special relativity, right, we are supposed to be talking about objects moving very, very fast compared to the speed of light, and then when object moving very, very slow, everything come back to Newtonian mechanics. But according to this calculation, object going zero velocity, so object going to zero velocity, we got a result here that was not noticed anywhere by Newtonian mechanics, and is this term over here, E equals mc squared. Even though object moving zero velocity in equilibrium, Newtonian mechanics is there, but the energy is stored inside this particle. And we only realize this by using special relativity, speed of light, things like that, and then come down to zero velocity back. So that is kind of a very powerful and far-reaching consequences that initially that is kind of surprising, and that is why this formula is very famous. Right? It's not just I know, like outside of physics, right, we always frame this equation as something that Einstein says, right? Einstein said this, and it's because of this, so that's why Einstein is very smart and famous. And why? So now we know why, right? We have gone through the similar procedure as he did, calculating the work done, and understanding why makes it even more interesting, right? Because special relativity is supposed to be moving fast velocity, but we still get a result for object with zero velocity. And zero velocity case, a new formula that was not discovered in Newtonian mechanics any time before Einstein. So that is why this, that is the original reason why this equation is very significant and very surprising, right? It is a big discovery by Einstein. Okay. No, that's why it's not denoted. It's not. So we can't say it's a kinetic energy. We are not calling this the kinetic energy. We will do kinetic energy after this. Okay. If we were doing long time ago, right, in week 3 and 4, in week 3 and 4, right, after we integrate, we call our integral to be the kinetic energy, right? That's how we got the work energy theorem. Remember? Long time ago. It's so long ago, right? If you forget, never mind, because we don't want to confuse ourselves. We don't call this a kinetic energy, but it is some energy. The unit is in joules, so it is some quantity here. Okay. Not the potential energy. Sort of, yes. I mean, that's an interesting way to put it. Yeah, it's not wrong, but it's not it's not a common definition to put it this way, but it's not wrong. Yeah. Correct. Yeah. So also not the most, but the total amount of energy, right? It's the total energy. It depends on the velocity. So the faster you go, the higher energy you have. Until you reach very close to the speed of light, E can be arbitrarily large. So it can be infinity. Okay. Any other question? So that's interesting, right? So a object that is, whether the particle is moving or not, right, it still contains some energy, and that is the energy stored inside the particle, and we kind of derive this based on the postulates of special relativity. Yeah. I don't think it's hard to stress how kind of surprising this result is, because it's like we are calculating two different unrelated situations. Well, it is related by taking the limit v goes to 0, and then we got this result. Then yeah, E equals mc squared. String theory, no. Yes and no. String theory is attempting, well, not the rest energy. So rest energy, I don't think it can be explained by string theory. Yeah. And I think right nowadays, people are getting more and more less confident about string theory, because there hasn't been any much progress in string theory for the past 10 years. So even if it claims to explain, I don't know if it can be a workable explanation or not. Right? It's one of the many theories of quantum gravity. So yeah. So in a broader sense, right, string theory is trying to derive relativity from some kind of fundamental concept. So in that sense, yes, it is one, in some sense you can say it's coming from, it can be explained from string theory, but is string theory correct? I'm not sure. That is a difficult question. Yeah. String theory is very messy at the moment. So even if it's correct, right, we need to refine the theory much more. A lot more work needs to be done, and that is the big challenge nowadays. Okay, so yeah, so I guess we can let this sit here, and we can take a break. So if you have any more questions, you can ask it over here. One thing that we still haven't done yet, right, is, okay, this is the total energy. We can't call this the kinetic energy. So where is the kinetic energy? So let us do that after the break. Yeah, people get straight of string theory. It's kind of true. So let us take a 10 minutes break, and we shall figure out the relativistic kinetic energy after we come back. So 10 minutes, we shall stop recording. Yes, this is Baki's book. The quantum finance, and the picture he chose is the KLCC. I guess at the time KLCC was still the tallest tower in the world, and this author was my PhD supervisor. No, my PhD examiner. I was quite scared of him. Okay. So now let's talk about, okay, where is the kinetic energy of the system? Okay, so now since this is the zero energy case, right, then what we can do is, well, we shall just define, because this is since mc squared is the rest energy, okay, so we subtract it from E, and then this should give the kinetic energy right? Because this is the part of the energy that is related to zero velocity, right? So zero velocity, you got this energy. Then this is the total energy. So if I minus the rest energy, then the remaining part shall be associated with motion. So that shall be our definition for the kinetic energy. So we shall have the relativistic kinetic energy. So relativistic kinetic energy is defined as K is equals to the total energy minus mc squared. In other words, it is c squared over 1 minus v squared over c squared minus mc squared. Okay, so obviously here we can check that if velocity is 0, v is equal to 0, then k is equal to 0 because mc squared minus mc squared. So this is consistent with the concept of the energy related to motion, right? So this is the relativistic kinetic energy. So so now, right, we can now consider the work energy theorem. So we can derive the work energy theorem because now we have the kinetic energy. Remember what was work energy theorem about? Work energy theorem is related to the change in kinetic energy, right? What we do have is our work energy is change of two energies, so it's still consistent. Maybe you can see it already, but I shall write it out explicitly. So deriving the work energy theorem for special relativity, right? So earlier we have calculated that the work done on the system is mc squared over the energy 2 at velocity 2 and then minus mc squared and then 1 minus velocity 1 square over c squared. So this is the total energy of the system, but to get kinetic energy I need to subtract mc squared. So what I can do is, well, let's look at this. Okay, so if I put it this way, if I minus mc squared here and then if I minus mc squared here, so this equation is still true because these two mc squared will cancel out, and this is why we got kinetic energy at velocity 2 and kinetic energy at velocity 1. So we still have the work energy theorem of the particle. So the rest energy is constant, right? So it's like integration constant. So constant minus constant gone, right? The same value of the constant, so it doesn't matter. It's not affected. So another way of saying is that the rest energy of system is something like an integration constant that comes out of your relativistic work done. Okay, so in any case, we still have the work done in the for the relativistic case. So work done is the change in relativistic kinetic energy. So we can still say it like this. Okay. So no, yeah, so according to our result, it's not mv squared, but is this longer formula. So actually this is something we can check. This is so different from half mv squared, so can we make it consistent with Newtonian mechanics? Because to come back to Newtonian mechanics, right, we need to slow down the particle. When the particle is very, very slow, we should get back the formulas related to Newtonian mechanics. So can we get it here or not? So this is what we can check. So again, checking the non-relativistic limit. Okay, so the non-relativistic limit. Okay, which is to say that when v is much, much slower than the speed of light, then v over c is a small number. And if it's a small number, we can neglect some factors, right? So let us see for the kinetic energy. So the kinetic energy, right, is written in this form. So I got mc squared over 1 minus v squared over c squared minus mc squared. So this is our definition of kinetic energy. Let me rearrange the terms. So let me put this in front. And then this term, I will write it in this way. So this term is mc squared, 1 minus v squared over c squared to the power negative half, correct? Okay. So what we're going to do is the binomial expansion. Everyone knows binomial expansion, right? I will do the binomial expansion. Yeah, and I think the math student may have already learned Taylor expansion. Actually, in the calculus one also got learned Taylor expansion already, right? So Taylor expansion of this term. So this is 1 plus if I just use the binomial formula, I got this, right? And then minus half minus 3 over 2 factorial minus b squared over c square, and then plus all these higher powers are, so 4 and then power 5, power 6, and so on and so forth. But if this is a small number, then the higher and higher powers will become negligible, so I don't need to write all of them. Okay, so let me simplify this a bit. So what I have now is mc squared plus mc squared bracket minus minus cancel out, so I got plus v squared over 2c squared, positive and positive, so everyone here is positive, 3 over 2 times 2 times 2, so it's 3 over 8, and then v4 over c4, and then something, yeah, so all these higher powers will be negligible. Okay, so all these higher powers will be negligible, and let me multiply these factors inside. So I got mc squared here, and then I got, so mc squared v squared over 2c squared, so therefore this will become cancel. So we see a half mv squared appearing here, right? What about the rest? So I got 3 over 8 mc squared v4 over c4, so this will become c squared, and then these terms over here. Okay, so mc squared minus mc squared cancel each other, then what I have here is k is half mv squared, and then all this other extra stuff is 3 over 8 mv4 over c squared, and all these higher terms. So remember, right, we're talking about v over c being a small number, so anything with v over c can be negligible. So negligible if v is much smaller than c, right? Because v over c will become a small number, right? So it's going to be negligible. So k comes back to my original half mv squared formula if v is much smaller than c squared. So we come back to the Newtonian kinetic energy. So actually, yeah, it does correspond to the kinetic energy that we are very familiar with. So half mv squared. No Taylors in calculus 1, is it? Oh, then I will call this a binomial expansion. Binomial expansion. So I think you learn it in calculus 2, is it? Yeah, never mind. No need to think so much. This is binomial expansion. Binomial expansion. Binomial series. I learned this in high school in STPM, so I don't know if you guys got learn it in your high school or not. Okay, any other question? So binomial expansion is equivalent to Taylor expansion. Yeah, so we got used this in the quiz as but I gave you the formula for the series, right, for the sine theta, cos theta. So yeah, yeah, binomial expansion. So that means instead of writing this full form, we shall write this as a long series. And actually, the reason why we do this is because, well, even if you write this as a long series, all this power, all these higher terms are negligible. So if we neglect all the terms, then the remaining term left here is just half mv squared. Yeah, so that is the that is our conclusion here. So we recover our Newtonian mechanics. Okay, so again, right, let's see. Okay, so now let me explain again why can't we accelerate to an object beyond the speed of light. So this is another reason, right? So another reason why particles can't reach speed of light. Okay, so yeah, so this part is done, right? So this part is done. Now I go to the next thing. Why can't we reach the speed of light? I'm recording, yes. Okay, so why can't we reach the speed of light? Okay, so yeah, so we use this formula again. So our calculation result that we got is well, 1 over v2 square over c square, and then minus mc square over 1 minus v1 square over c square. Okay, so if we want to reach the speed of light, right, so to reach speed of light, I want v2 to be equal to the speed of light, right? So if you want v2 to reach the speed of light, what happens to this? This becomes infinity, right? So it turns out that taking the limit of v2 approaching to the speed of light is actually, the work done turns out to be infinity. Okay, so mc square 1 minus v2 square over c square. This term is independent of v2, so any initial velocity doesn't matter, right? So it doesn't matter what is your initial velocity, but if I want to reach the speed of light, this work done is infinity. So need infinite work. Work done is the transfer of energy, right? So I need to transfer energy to accelerate the object into the speed of light. So needs infinite energy to reach speed of light. Okay, so that is the reason why. So we can't go to the speed of light like this. Oh yeah, I wrote the wrong thing. See. No, this is 5, 6. Correct. If we have no mass, then we can reach c. Why? Because if m is 0, then you can take a limit of c to infinity, then maybe, right, maybe you can reach c. And that is why light can travel at the speed of light, because light, right, photons are massless particles, so massless particles can reach the speed of light. So massless particles like photons, yeah, gravitational waves, gravitons, all those things, they can reach the speed of light. Okay. So now we want to derive a formula that is relating the energy with the momentum. So deriving a formula relating energy to momentum. Okay, so yes, we have calculated the energy. We have derived the formula of the energy of a particle of mass m moving at speed v to be mc squared over 1 minus v squared over c squared and then the square root, right? And also we have obtained the relativistic momentum to be p is equal to mv over 1 minus v squared over c squared. Okay, so I want to find a formula that will relate these two together. So what I'm going to do is let me square both sides of the equation. So over here I got m2c4 squaring this, and squaring this will open the square root, right? And then I bring this down. So this is equation 1, and I shall do the same here. So if I open the square, I got mv square over here and then 1 minus v squared over c square. So if I bring this down, is 1 over v squared over c square. So this is equation 2, right? So what I'm going to do is I shall actually to match these two, right? So what I'm going to do is hang on a second. So what I'm going to do is I'm going to p squared over m square. Wait, let me modify this a little bit first. So I got v squared over here, okay, and then I shall times c squared over c squared. Okay, then I shall bring this down. So I got p squared over m square c square, and then on the right hand side is v squared over c square. Yeah, now I can now I got something that will cancel later. Okay, so now I shall call this equation 2. Okay, so I got these two equations now from manipulating the equations for energy and momentum, and then I'm going to take equation 1 minus equation 2. So equation 1 minus equation, so this minus this, minus p squared over m2c2, and then this minus this. So both of them have the same denominator, and I got 1 minus v squared over c squared. So this is actually just 1, right? So then I shall simplify this equation. 1 plus p squared over m2c2, so that my e square is equal to m2c4 plus p square c square, right? So finally I got the expression that is relating energy to momentum. So m2c4 is just mc square, and then this is pc square, and then this is the energy. Okay, so this is the formula that is relating energy to momentum, right? So for example, the special case of this is a quite important formula, and you will use this formula again in modern physics later, so that will be important as well. Okay, so we have derived this formula assuming a particle of mass m, but just now you also said, right, when the mass is 0, it can travel at the speed of light. Everything is contained inside here. So for a particle of mass m, and it's stationary, that means p is equal to 0. Then you got p is equal to 0, so E is equal to mc squared. Okay, so you got this case. That was what we got just now, right? And then for massless particles, m is equal to 0. So the energy of a massless particle is pc. Okay, so this massless particle, this will be obeyed by photons. So you will learn this probably in next semester. Next semester you will learn that the light is an electromagnetic wave, and then sometimes we treat it like a particle called the photon. Electromagnetic wave will carry momentum called the Poynting vector, right? It's related to the Poynting vector, and we can calculate the momentum of a photon. So the energy of a photon having momentum p is given by this relation over here. Okay, so this is the results that we got. Yeah, so that is the we call this the invariance, the Lorentz invariance formula related carried by a particle, whether it's massless or having mass. No, so that's the thing. You need m equals to 0 exactly. If for a light particle, right? Any particle that is non-zero mass, even the mass is very small, if it's not exactly 0, you cannot reach the speed of light. Okay, so if even if m is a very small number but non-zero, okay, even if m is small but non-zero, so even if like 0.0001, if you take this limit, you will still get infinity unless m is immediately 0 exactly. If the whole m is 0, then yeah, then you can't reach the speed of light. So even if you lose weight, right, you still can't, because your weight is going to be non-zero no matter what. So that is why. Yeah, so little mass electron still cannot go the speed of light. Quarks or anything with mass, so we can't go to the speed of light. Okay, so let us work an example. 10.4.1. So the concept is, as you can see, right, the concept is very complicated, but the example most of the time is very simple. The problem is to figure out what is the correct variable to substitute in, right? That is the biggest problem here. But once you substitute the correct variables, the rest is just finishing off the calculation. Okay, so we are doing example 10.4.1. Let me read the question. Okay, so I have two protons, so the mass of the proton is given, right? So this is the mass. It's not relativistic mass or whatever, it's the mass, right? Mass is mass. Are initially moving equal to opposite directions, so they're moving equal to opposite directions, so they collide head on, face to face, and the collision produces a neutral pion. We assume all three particles are at rest after collision, obviously relative to the laboratory, and energy is conserved. So hang on, I guess there's a missing sentence. We want to calculate the speed of the particles before collision. So yeah, I'm sorry, there's a missing sentence over here. So what we want to do now is to calculate the speed of the particles before collision. So the masses are given, right? So the mass, what time is it now? Okay, so the mass of each proton is 1.67 times 10 to the 27 kg. The mass of the pion is a new particle is 2.4 times 10 to the 28 kg. And then we want to calculate the speed of the velocity relative to frame before collision. So so first of all, we can use the question say energy is conserved, so let's look at the total energy before collision. So my initial energy, so I call this E initial, is just what? Well, it's only two protons moving. So I have two protons in the system, so 2 times energy of the proton. And then the total energy is given by mc square over 1 minus v square over c square. So the mass is mass of the proton. So this is a number that you can calculate, right? In terms of v. So v is unknown, so we want to calculate the v here. Total energy after collision. So I shall call this the final energy, E final. And I have 3 particles at rest, right? So after collide, the 2 protons remain at rest. And then a pion is created also at rest. So we shall calculate this as the energy of 2 protons at rest. And the energy of the pion also at rest. The question says everything is at rest after collision. So it's just 2 mass of the proton c square plus mass of the pion c square. So by the conservation of energy, this total should be equal to this total. Okay, so energy is conserved. Okay, so we conclude that m proton c square over 1 minus v square c square is equals to 2mp c square plus m pion c square. So we can try to simplify this equation. Well, we can cancel the c, right? So we can bring this gamma factor up. So I got 1 minus v square over c square. And then this is m proton, 2m proton plus m pion. So I can simplify this factor a bit. I got 2 plus m pion over m proton. Hang on, 2, I forgot the 2. Yeah, so 2. So there's a 2, so I can cancel the 2 also. So I got 1 minus v square over c square is equals to 1 over 1 plus m pion divided by 2m proton. So all these are numbers which can be plugged in and calculated, so it shouldn't be a problem. If you put in the numbers, right, it's going to be 1 plus m proton, so m pion, sorry, 2.4 times 28, and then proton is 2 times 1.67 times 10 to the 27. I forgot the square root, right? Yeah, I forgot the square root. So if I calculate all this, I will get v squared over c squared. Square both sides. Once you get this number, you square both sides, you're going to get 0.8704. So v squared over c squared is going to be 1 minus of this, so it's 0.2355. So v is equal to 0.360 times the speed of light. So it's 36% the speed of light. Yeah, so this is something that we learn. That is why the momentum equals to mv is for Newtonian mechanics. Photons has 0 mass but still got momentum. We will, yeah, so this is something that will be done in detail in the electromagnetism course. So there's 2 ways to think about it. If you talk about modern physics, quantum mechanics, you got wave-particle duality, right? Using the wavelengths, we can calculate the momentum. But even in classical electromagnetism, we solve the wave equation. From there, we can calculate the momentum of the photon as well. So yeah, the momentum is not defined as mv. Yeah, we can consider it, yeah, considering as wave. So because like the wave-particle duality, right? P is equals to h over lambda. This is the Planck's constant. So if you know the wavelength of the photon, you can calculate the momentum. This is the de Broglie formula. Actually, I don't need to talk too much about it. You will spend a lot of time learning this in the next semester, the modern physics course. For the physics student lah. So the MAT student, if you're interested, you can take this course as well, or the electromagnetism course. So the electromagnetism course is the Poynting vector. So S is proportional to E cross B. Yeah, then we will do all the calculations related to that. Okay. Yeah, so that's it. We are almost finishing everything in the special relativity already. The last one, right, is I do not intend this to be examinable, but for future courses, right, to learn higher level courses is going to be important. So it is related to some fundamental aspects in physics, so and almost philosophical questions. So I would think it would be interesting for us to talk about today as a final topic. What I'm talking about here is space-time diagram. I think, did we discuss this before? The Hawking's book, The Brief History of Time, got talked about space-time diagrams a bit, I think. And yeah, the brief history. The other one probably, I don't know. I don't think so. But let us talk about space-time diagram. Okay, so right now, right, we are still using a single frame S. So don't need Lorentz transformation yet. So now just use a frame S. So an event will have 4 values, right? Is t, x, y, z. So for space-time diagram, right, it is a 2-dimensional, because we can only draw it on a piece of paper, so it has to be 2-dimensional. So we just draw the t and x direction. So we're going to plot the t and x graph. So the space-time diagram is plotting the t and x coordinate. Okay, so what is a space-time diagram? Let us consider frame S, right? We are Alice in frame S. We are observing the motion of a particle. Okay, so what is the particle doing? Well, a particle, right, will have different x at different t. So that is already true in mechanics. So let us consider this. A particle, right, it can be either moving or not moving in S, can be represented by a curve on the tx plane. Okay, so that is already true in chapter 1, right? We have done this in chapter 1. Chapter 1, we plotted t against x. The only difference is we use t as the vertical axis now. So these curves are called world lines. Since some of you got read up on string theory before, right? So in string theory, you might have seen something called world sheets. So in string theory, instead of a particle, we consider the string. But right now, not string theory. Right now, we talk about particle. Okay, so particle is a world line. It's a 0-dimensional object moving on the tx plane. String theory is a 1-dimensional string moving on the tx plane. So that's why it's called the world sheet. Okay, so we plot the motion of the particle in the tx plane. No need open cam. No need. Yeah. Okay, so no need open cam. So actually it's nothing complicated, even though we use like very fancy language, right? I think it's quite simple, because if I draw this line, right? If I draw a straight vertical line, do you know what I mean? Over here. Right, a straight line, right? It means that the position, if a particle P is moving on this straight line, right, that means the position is always the same value. The time always has to move forward. So obviously, right? So this is a stationary particle. Relative to Alice. That means frame S. We are using the coordinate system of Alice, right? So if I draw this kind of particle, so if a particle is moving like this is a moving particle, right? So at different time you got different positions. So this is a moving particle. So over here we got a moving particle. And then the important thing I want to focus on right now is, okay, so if the moving particle, what is the tangent of this line? So the tangent of this line is something to do with the velocity of the particle. So the tangent of the curve, so the tangent, so let me draw a new line here. So the tangent of the world line is 1 over velocity. Makes sense, right? Because if I plot this on the tx plane, right, and then I have a particle that is moving, okay, so I got, let's say at this moment and at this place, I got a tangent. So the slope of the tangent is, remember t is my vertical axis, so this is actually dt dx. So dt dx is 1 over dx dt. So this is actually 1 over v. Okay, so in other words, slope of tangent, let's call this point A, at point A is equals to 1 over the velocity at point A. Okay, so from here we can distinguish the few cases, right? That's the velocity. So the velocity can be faster or slower than the speed of light, which is what we'll consider this. So the vibration of the string turns energy into mass. Actually, I don't know. I think so, yeah. The frequency of the vibration will tell you the type of particle of that thing. So the type of particle will definitely be related to the mass of the particle, and frequency also will be related to the energy. So I think that, yeah, in that sense that's true, yeah. So the frequency will be related to the particle, I mean the mass. Frequency of the string vibration will be related to the mass. Okay, so yeah, so now let's see, right, the three cases of slope. So if the slope, right, if the slope is higher than 1 over c. Okay, so if the slope is higher than 1 over c, what does it mean? So then if it's higher than 1 over c, that means it is moving slower than light. So if the slope of the tangent is exactly 1 over c, this is the particle slowing at the speed of light. And if it's smaller than 1 over c, it is faster than light. And as we have calculated many times, right, nothing can travel faster than the speed of light, right? So using Lorentz transformation, using the relativistic force, using the relativistic work done, it seems like you need infinite work done or infinite force, everything infinite to reach speed of light. So this part is impossible. So that means, right, the type of world lines that can exist on the space-time diagram, everything must have the slope that is smaller than the speed of light. So at most is exactly the speed of light. That is for massless particles. Okay, so then we can see that everything is contained inside a light cone. What time is it now? Okay. Yeah, so that means, right, so since nothing can travel faster than light, right, all world lines have tangents greater than 1 over c. Okay, so now I'm about to define the concept of a light cone. So then, in other words, right, all world lines that passes through an event P must be contained in a cone. So what do I mean here? So let's say, right, okay, let me plot my space-time. So this is my position, and vertically is my time. Okay, so doesn't matter where's the origin, but let's say I have an event P. Okay, so over here I got that event P. So something happening with a time coordinate and something at some position. So everything that started from event P, right, must be moving inside this diagram. Okay, so the slope over here is 1 over c. The slope over here is negative 1 over c. So everything that is related to event P, right, must be contained within this cone. So anything that passes through an event P must be slower than the speed of light, so the world line. Okay, so that means if I have something that traveling like this is impossible. Okay, so it must be slower than the speed of light. So this shaded region is the light cone. So why is the light cone important? The light cone, right, is well, running short of time. I'll quickly say this. We can continue this on Wednesday. We can discuss the concept of causal connection. Okay, so that means, right, because nothing can travel faster than light, we cannot transmit information faster than light, or anything that starts from an event cannot reach another point if it's going faster than light. So what I'm trying to say is an event P can influence another I would say future. So I will continue the rest on Wednesday. Future event Q only if Q lies in the light cone of P. Okay, so let's say I have P, right, an event P, and then I got the light cone. So everything that starts from P can only happen inside this region. Okay, so if I have an event Q over here, Q1 over here, and Q2 over here, only Q1 can be affected by P, because whatever happened, I can transmit a signal to Q. I cannot transmit anything towards Q2. Okay, so what we can say is Q1 is causally connected to P, and then Q2 is causally disconnected from P. Okay, so whatever Q2 is like separate. So why I say like space-time diagram is like some philosophical thing, if you think about it, is because whatever happens to P and Q are like in different regions. Whatever happens to P, Q2 will never know, right? Whatever reality is in P2 is not relevant because they are not causally connected. Okay, but between P and event Q1, then yes, so they are connected. Okay, so anything that's inside the light cone, they exist together, they can affect each other, causally connected. If they're outside the light cone, then whatever happens there cannot affect here. So that is the distinction between the two. Okay, so to think about it, right, the concept of black holes is also everything inside the black hole is outside our light cone. So whatever that is dropped into the black hole, it cannot affect us anymore. We are no longer in the same light cone anymore, and that is why things that fall into the black hole is gone forever. Nothing, as you can't travel faster than light, so nothing can come out of the black hole anymore. So that is why we have this style of space-time diagrams. Okay, we have actually I actually have more simpler examples to explain this, but I guess we can continue this on Wednesday. So yeah, because it's quite late already, right? Yes, you can treat, this is why black hole is like a trash disposal, because you throw it into the black hole, you can forget about it, it's gone forever. Yeah, so I think that's all for today, so let me stop the recording. I expected to end early, but still